Okay, so I'm start recording already. Okay, so electromagnetic induction, yeah, for chapter 5. So first of all, you must know what is magnetic flux lah. Yeah, magnetic flux, we have learned already. It is the number of magnetic field lines passing through a certain area. Okay, and this is the formula for magnetic flux. Okay, influenced by magnetic field strength, area, and also the theta. Angle theta is the orientation of the plane lah. Yeah, angle between the normal and the magnetic field line. Okay, that's theta. So all these factors affect the number of magnetic field lines passing through the area, or we call it magnetic flux. Okay, so and then we have magnetic flux linkage. If we have multiple turns, then we multiply n. Then that we have magnetic flux linkage. Okay, so now let's talk about the following part. Okay, induced EMF. Induced EMF means we generate electric. Yeah, we generate electric. So it is explained by Faraday's experiment. Okay, so electromagnetic induction is the production of induced EMF or induced current whenever the magnetic flux through the coil, the loop, or circuit is changed. So how is the EMF or EMF generated, or electric generated? He say the key is if there is magnetic flux change. So the concept of magnetic flux is very important. So the concept of magnetic flux that we learned before is very important. Magnetic flux is the number of field lines passing through a certain area. So if this number of magnetic flux passing through the area change, berubah, then it will generate electric in the coil. This magnetic flux. So that's Faraday's law. Okay, flux change. For example, just look at this example. Consider some experiments by Michael Faraday that lead to discovery of Faraday law induction. You see, at first, this is the coil, isn't it? This is a coil with certain area. Okay, so here is the magnet. Give out the magnetic field lines. Give out the magnetic field lines. So if let's say there is no relative motion between the magnet and the loop, the galvanometer show no deflection, no induced current. That means if this magnet and this coil doesn't move, no electric is generated. Because why? Because the magnetic flux doesn't change. Magnetic flux through this area doesn't change. It maintains same magnetic flux. No change. But you see, B, if you move the magnet toward the loop, it increases the number of magnetic field lines passing through the area. It changes the magnetic flux. You compare the magnet at far away and magnet near to the coil. Of course, if you bring the magnet from far away to near to the magnet, the number of magnetic flux through the area increase. Because when far away, the flux less flux. When magnet is near to the coil, more flux. So there is if you bring the magnet from far away to near to the coil, there is a flux change, magnetic flux change through the area. So of course it will generate electric. Okay, and you move the magnet away also. If you move magnet away, that means flux decrease. Flux through the area decrease. If there is a decrease in flux, got flux change. Got flux change means got generate electric. Okay, so the conclusion is EMF is induced or electricity is generated when the magnetic flux through the coil changes. No change in magnetic flux. If there is no change in magnetic flux, then the electric cannot be generated. Or electromagnetic induction cannot occur. Okay, so electric is generated only when you have change of magnetic flux. Okay, so conclusion. If the magnetic field lines through the air through a coil, this is the magnetic flux changes, then induced EMF will exist. That means it will generate electric. Okay, it is also shown that the EMF induced will increase if you use a stronger magnet. If you push the magnet faster into the coil, yeah, you increase the speed of magnet, you increase the area, and you increase the number of turns. Yeah, also will increase the electricity generated. Okay, so this is the qualitative explanations. So let's move on to quantitative explanations. Yeah, so now let's talk a little bit more detail. Yeah, about this induced EMF. We have two law. One is Faraday's law. One is Lenz law. What's the difference, class? Okay, so I will use this here one note to explain. Okay, so now we are talking about induced EMF. Yeah, so let's write something. So we are talking about induced EMF. Induced EMF. Yeah, E induced. That means this is about what? Is about generate electricity lah. Generate electricity. Just now you are learning about what? You are learning about Faraday's experiment. This is Faraday's experiment. Michael Faraday discovered this. Okay, so we have Faraday's law. Okay, so let's write it down. We have Faraday's law. Because it is Faraday who discovered this phenomenon, so we must honor him. And then we have Lenz law. Okay, we have Lenz law. So Faraday's, yeah, he's talking about Faraday's law is used to determine the magnitude of induced EMF or induced current. Okay, it's talking about magnitude. That means how big is the electricity generated? How big? Lenz law is focusing on direction of induced direction of the induced EMF or induced current. This one is focusing on direction. So one is for magnitude, one is for direction. So equations, only Faraday's law has the equation. Yeah, Lenz law is only talking about direction, so it doesn't have equation. Okay, so what's the equation for Faraday's law? Equation for Faraday's law is, so E induced equal to negative d phi over dt. Okay, so actually this is this is d phi means is change of flux. Yeah, the top here, this is called the change of magnetic flux linkage. Change of magnetic flux linkage. So we can write the formula above as flux linkage final minus flux linkage initial. Got initial and final. Okay. Got initial and final, and then divided by time taken. Okay. Yeah. So and then we know that magnetic flux linkage is we know that magnetic flux linkage is actually n phi, isn't it? Because capital phi is for multiple turn, small letter phi is for one turn only. Yeah, one turn, one area only. So we can rewrite the formula as negative and d phi kecil over dt. Small letter phi. We can write it this way also. Understand, class? So that's it lah. Yeah. So we can use this. You see, we Faraday's equation. We can use this equation to find how big is the EMF. How big is the EMF? You know, you can find how big is the EMF, the magnitude of EMF. How big? Understand? Yeah, we have a formula to calculate the magnitude of induced EMF. Yeah, isn't that great? Yeah, isn't that wonderful? Yeah. And there's this negative. Yeah, you can see here there is a negative sign. This one is for Lenz law. This one is for Lenz law. Which concerns about direction. Yeah, I will talk about Lenz law later on. Okay, so this is the negative sign is for Lenz law lah, but the equation is for Faraday's law. Okay, so so here Faraday is talking about if there is a change in magnetic flux or magnetic flux linkage, then you will produce EMF. And then of course one more thing, induced EMF also, once you find the induced EMF, you can find the induced current. That means the current generated. This based on Ohm's law lah. Yeah, this based on Ohm's law, which is V equal to IR. Okay, V equal to IR. Yeah, V equal to IR. So E equal to IR. Okay, look at this example. For example, I give a situation. If let's say I have here you have a magnetic field. Let's look at here. Let's look at this example. Yeah, this example. So see how brilliant. Okay, so okay, this is a region with magnetic field. Okay, all these magnetic field direction. Okay, these are all the magnetic field direction. So right now, okay, let me. Okay, I want to have a coil. Let's say I have a coil. Second. Yeah, that'll be great. Here. Then go to here. Okay, go to here. Go to here. Yeah, maybe just here. And then here. Okay. Look at maybe I should draw. Maybe I draw a little bit more. Okay. Okay. Now class, let's move this coil. Yeah. They have coil at position 1, position 2, position 3, and position 4. Yeah. This is just a maybe a copper coil with certain area lah. Yeah, with certain area A. I bring this coil from here to 1 to 2, and then 2 to 3, and then 3 to 4. Class. So I want to ask you, class. I want to ask you. Now, if I bring the coil, yeah, are you listening, class? Are you listening? Are you listening? Yeah. You understand until here? Okay, good. Let's continue. So now, if I bring the copper coil from position 1 to position 2, okay, that means here, the outside, there's no magnetic field. I bring the coil to a region with magnetic field. Okay, is there any changes of magnetic flux through the coil? Is there any changes of magnetic flux through the coil? I've got changes of magnetic flux or not? Yeah, got change of magnetic flux or not from 1 to 2? I don't want, saya tak mau robot saya bukan cakap kepada manusia yang tak hidup bukan kepada benda saya bukan cakap ke dinding, saya nak manusia yang hidup di depan saya. From 1 to 2, I want you to give response. Yeah. It is because of irresponsiveness that's why your result is like that. Yeah. So from 1 to 2, okay. So what happened? Is there any change of magnetic flux through the area? Is there any change of magnetic flux through the area if I bring the coil from 1 to 2? It's so obvious, class. Is there any change of magnetic flux? Class? Only Ryan seorang kah? Yang lain? Patutlah Ryan dapat A ya. Yang lain saya itu tak dapat A ya. Saya tak tahu kenapa ya. Padahal saya sudah rasa apa yang saya ajar itu sudah cukup untuk kamu dapat A+ sudah. So that means your thumbs up means what? That means is it got flux change or no flux change? At least you buka mic cakap lah. Yeah? If no response, I end the session class. I end right away
Change, sir.
Got change Yeah. So that means from 1 to 2, I bring the coil from 1 to 2, there is a flux change. Yeah? Got flux change. Good. So, so there's a flux change. That's why I got change of magnetic flux. Yeah? When there is a change of magnetic flux, yeah, from 1 to 2, then it will generate electric. Yeah? For this case, here the flux increase. Yeah? If you look at here, the flux has increased. From 1 to 2, the flux, like originally no flux, go to 2, that means flux increase to 4 lines lah, you see? Flux increase. There's change of magnetic flux. So just as simple as that, there's flux change when you move coil 1 to from position 1 to position 2. There's flux increase, got change of flux. So because got change of flux, just that simple, this coil will generate electric. It will generate electric. But in what direction? In what direction? The current will flow clockwise or anti-clockwise? That one we have to ask Lenz law. Lenz law, yeah? So, by the way, I already know the answer of the direction. So, let me look at it again. So, this one is increase. So, I have to decrease. So, opposite direction. So, that means current will move anti-clockwise. Why is it not clockwise? Current will move anti-clockwise. How do I find out the current is anti-clockwise but not clockwise? Aren't you surprised that how I can get this direction? You don't want to learn? Huh? If you want to know how I know if this one is anti-clockwise, then you must listen. And you must give response also. Not just listen, yeah? Listen, even the wall also can listen. The wall also listening to me all the time. Yeah? Listening passively. But you are not the wall. You are human. So this one is the current is moving anti-clockwise. Yeah? How I know this? That one you have to ask Lenz law. Okay? So if I move the coil from position 2 to position 3, what happened, class? Is there any change of magnetic flux? This region has the constant magnetic field strength. If I just move it from position 2 to position 3, is there any change of magnetic flux through the coil? Come on, you have a mouth. We use mouth to eat. Besides eating, what do we use it for? If I move the coil from position 2 to position 3, what happened? Is there any change of magnetic flux? Just say yes or no.
No.
Yeah, no change of magnetic flux. So no change of magnetic flux, 2 to 3. Is there any will it generate any electric in the coil? Will it generate any electric in the coil? That means if the flux change is that means if the flux change, the delta phi is 0, what happened to induced EMF, class? What happened?
0.
Yeah,
0.
0. So that's right. Yeah, 0. So there is no induced EMF. Yeah, when induced EMF is 0, that means current induced also 0. Okay, so there's no current induced. Yeah, so if you move 2 to 3, the although the coil still have magnetic flux, but the flux doesn't change. The flux doesn't change, so no current induced. That's why in this experiment, if you don't move, no relative motion between the magnet and the loop, that means the no current induced, because the magnetic flux is constant through the coil. Unless you move the magnet towards the coil or away from the coil, then if you move it magnet towards the coil, then your flux increase. If you move the magnet away, then got flux decrease, got change of flux. Got change of flux, then only got induced current. If you just maintain the magnet at same position, coil at same position, that means the magnetic field strength through the coil, magnetic flux through the coil is still the same. It's just the same as this example. Although I move this coil inside the magnetic field, but this magnetic field maintain the constant magnetic field strength. Yeah, constant magnetic field strength. So the magnetic flux through the coil is still the same. Like you see this one, the magnetic flux through the coil is like 4 lines. This coil also 4 lines. No change of magnetic flux, isn't it? The flux is constant. Or I can the flux is constant. Yeah. Or we can say the delta phi is 0. Delta phi is 0. Change of flux is 0. The flux is constant. So no induced current. No current in the coil 3. No current. Okay. So now if I move this coil from position 3, go out to position 4. Go out from the magnetic field region. Yeah, so got from area with magnetic flux to area with no magnetic flux. Is there any change of flux, class? Is there any change of flux? Got change of flux or not?
Yes.
Yes, got change of flux. The flux decrease. Tak penting, tak kira menaik ke menurun, asalkan ada perubahan. Asalkan ada perubahan flux, tak kira meningkat atau menurun, dia akan generate elektrik. Flux meningkat atau flux menurun menurun pun akan generate elektrik. Cuma kalau ini meningkat, dia punya current dalam anti-clockwise. Kalau menurun, flux dia akan current dia akan jadi clockwise. Dia memang begitu. Jadi opposite direction. Kenapa jadi opposite direction? Itu kena tanya Lenz law. Ya? Kena tanya Lenz law. Tapi bila Lenz law sedang bercakap, you kena dengar lah. Bila Lenz law sedang bercakap, you kena dengar lah. Kalau you tak dengar, Lenz law cakap berapa banyak pun, you tak akan faham. Ya? Gitu. So, dia current dia akan jadi anti-clockwise lah. So, itulah dia. Okay? So, that's simple as that. How to generate electric. Yeah, how to generate electric is as long as you have as simple as if you have change of magnetic flux, you will generate electric. Once you have generate EMF, then you will generate induced current also. The key is change of magnetic flux. What is this? The key is change of magnetic flux through a coil. Okay. Now I want to talk about Lenz law. Yeah, I want to talk about Lenz law. So how do I find out that this one is anti-clockwise and this one is clockwise? How do I find out the direction of induced EMF? Just now Faraday's is we can use this formula to calculate the magnitude of induced EMF and also magnitude of induced current. But to talk about direction of anti-clockwise or clockwise, that one is Lenz law. Yeah, and also the negative sign here, it carries the meaning of Lenz law. Okay, carries the meaning of Lenz law. Okay, so let us first look at the notes. What is Lenz law about? See that? Lenz law Lenz law states that the induced current will flow in a direction such that the magnetic field produced by the induced current will always oppose the changing magnetic flux that produces the induced current. Baca betul-betul. Kalau you rasa confusing, baca lagi sekali. Induced current will flow in a direction. Flow in what direction? The induced current will flow in what direction? Such that means a condition. Ya, condition. Apa condition dia? Magnetic field produced by the induced current will oppose the change of magnetic flux that produces the current. So that means this induced current yang generate itu, dia akan produce another magnetic field or another magnetic flux to oppose the change of magnetic flux that produces the current. Okay, so saya simpulkan begini. Ya, kalau you rasa tak faham, saya simpulkan begini. Lenz law says the direction of induced current is always oppose. Perkataan oppose, mungkin huruf besar kalau tak nampak. Ya, oppose. Oppose what? Oppose the change of magnetic flux that causing it or producing it. Why do we say change of flux that producing it? Producing what? Producing the induced current lah. Producing what? Produce the induced current or induced EMF. Who is causing the induced EMF? Who is causing? Who is the cause? The change of magnetic flux. The change of magnetic flux are causing this induced EMF to happen. You see? That is Faraday's law. Faraday's law, he says, is the change of magnetic flux that causing the induced EMF, that causing the induced current. Understand? It is a change of magnetic flux that causing or producing the induced current. Is what I mean. Oppose the changing magnetic flux that produces the induced current. You understand? So changing magnetic flux is the cause. Why we have induced current in the first place? Why do we have induced current in the first place? It is because of changing magnetic flux. Changing magnetic flux is the cause. It's the reason. It's the reason why this induced current is produced. Understand? It's a reason. As simple as that. It's a change of magnetic flux that produce the induced current. Now, how is the direction of induced current? The word is oppose. Oppose. The direction of induced current must oppose the change of magnetic flux. How do we understand this? Oppose. Okay, like this, class. Look at here. Also, I need to put a table. Yeah, I need to put a table. So to understand more about this phenomenon, and you must listen attentively. Yeah, even if I explain 1,000 times better, but if you don't listen carefully, what's the apa gunanya? Sudahlah guna teknologi semua ni, ya. Tulis gambar semua. Tak faham lagi. Bukan tak faham. Kamu sudah faham sekarang, tapi masa exam lupa semua. Apa guna? Sekarang faham, tapi exam nanti dapat kosong markah? Itu maksudnya tak usaha. Masa exam itu tak betul-betul belajar. Saya suruh you buat soalan tambahan dalam nota kuliah. Ada tak you buat? You sudah tak buat soalan tambahan dalam nota kuliah semua? Ada tak? Atau you bergantung pada soalan tutorial saja? Mana cukup makan? Mana cukup latihan semua? Sekarang faham, nanti lupa. Apa guna? Tolong fikirkan balik. You buat berapa? You punya usaha sampai mana? Don't point your finger to the lecturer ke? Apa ke? So this one talk about change of magnetic flux. Okay. So now the induced current, the oppose, the change. The word oppose. This is the change. The change in magnetic flux lah. Yeah, change in magnetic flux. Yeah, the change in magnetic flux. So talk about change of magnetic flux. Yeah. Okay. Oppose. Oppose is Lenz law. Okay. Lenz law. Now, class, look at we see induced current happen only when I bring the coil into the magnetic field and also I bring the coil out of magnetic field. That it will induce current. But what direction? Why is it anti-clockwise and here is clockwise? Why? So look at here. So for this happened during one, yeah, especially one go to two, and then happen when three going to four. Yeah, three have this happened. So I make two. You know, two situation. Yeah. From 1 to 2. From 1 to 2, what is the change of magnetic flux? Yeah. Maybe I should put this like this one. Yeah, I should put the flux external. Yeah. I should put yeah. This is the flux. I should put it this way. The flux external. Yeah. This is a flux external. Yeah. Flux external. This is the flux external. Yeah. Okay. This flux is given by outside lah. The flux that passes through this area, is given by outside, external. I say it's external magnetic flux through the coil. Yeah, so the external magnetic flux through the coil increases if I bring the coil from position 1 to position 2. So the flux increases, isn't it, class? For position 3 to position 4, the external flux decreases. So, okay, please write it down here. So kalau from 1 go to 2, the flux external increases. The external flux increases. Kalau 3 to 4, external flux decreases. Menurun lah, dia menurun. Yang 1 to 2 meningkat, kan? So this is the change. Delta, change yang berlaku. Ini meningkat, ini menurun. Kan? Betul tak? Lenz law cakap apa? Menentang perubahan. Ya, saya ulang. Oppose means menentang. Menentang apa? Menentang perubahan. Apa perubahan yang berlaku? What changes happening in position 1 to position 2? What changes happening? Increases. The flux external increases. So Lenz law says oppose the increase. Oppose, menentang perubahan ini. Dia tidak mahu dia meningkat. Pendek kata, coil ini tidak mahu flux external ini meningkat. So macam mana dia tak mahu dia meningkat? How he oppose the increase of magnetic flux? He tried to decrease the flux. So write down. So now coil, okay, coil. Write down. Maybe I should just type it. Yeah, I just type it. Yeah, coil. Okay, I should make it bigger. The word. Tak ajar sampai macam ini, tapi masih disappointing. Yeah, very disappointing class. Sudah usaha macam ini, tapi macam seolah-olah tak nampak. Ya. The end bagi saya ya. B minus. Sebab tak tahu you belajar macam mana. Ya. Think I should just use this color lah. Okay. So coil wants to oppose the change. How to oppose the change? Cause wants to decrease lah. Kalau dia meningkat, dia nak menurunkan lah. Ya, decrease the external flux. Try to decrease the external flux. So what happened? Yeah. So coil wants to decrease the external flux. So what happened, class? So coil produces or induces opposite. Dia produce opposite. Sebab dia nak decrease, dia produce opposite flux lah. Yeah, coil induces opposite flux. Opposite. Yeah, produce opposite. Nampak kah? Kasih besarkan. Coil produce opposite flux. Sebab kalau opposite flux, dia akan cancel each other. Opposite direction, dia cancel each other. Understand? So macam ini, kalau flux yang meningkat itu adalah ke dalam, opposite flux means dia keluar lah. Opposite flux dia keluar dari kertas. Understand? Dia keluar dari kertas. Ini flux bukan, yang grey itu ialah flux external. Tapi yang merah itu flux from the coil. Flux induces from the coil. There is a flux from the flux induced or flux from the coil. Understand? Ada dua jenis flux di sini. Satu flux external, satu flux induced by the coil. Understand? So dia adalah opposite direction. Now use your what? Yeah. So now use what? Use your right hand grip rule. Yeah. Now use your right hand grip rule. Masih ingat tak apa right hand grip rule? Right hand grip rule maksudnya okay, right hand grip rule. Right hand grip rule. So guna yang ini for magnetic field, yeah, or we can say magnetic field induced ataupun flux lah. Magnetic field itu macam magnetic flux, yeah, induced. And this one is for the finger is for induced current. Induced current. So use your right hand grip rule to determine the direction of, to determine what? To determine the direction of induced current. Induced current direction, Lenz law. See that? So just look at this is the thumb. The thumb is for induced flux. The induced flux is out of the paper, out of the page. Are you using your right hand now? Class, are you using your right hand or you just listen passively? I hope I cannot see you, but I can feel you. Your flux, your thumb should point out of the page right now. Your thumb should point out of the page right now. And then your finger point in what direction? Your forefinger point in what direction? Class, at least give me some response lah. Give me some response. Your thumb is pointing, your magnetic flux, the thumb pointing out of the page, and your finger point in what direction, class? Use your hand together. Come on. Don't waste the time. Your finger point in what direction? Your forefinger?
Out, sir.
Your thumb is pointing out of the page, so your forefinger point in what direction, class?
To it's putar-putar, sir.
Right, sir.
Huh?
Anti-clockwise.
Anti-clockwise, isn't it? I already draw there already. Yeah, even before you. So your thumb is pointing out of the page. Your thumb is the show the magnetic flux direction out of the page. So your forefinger is pointing anti-clockwise, isn't it, class? Isn't it?
Yes.
Induced current. Okay? Why like that? Because the coil want to decrease the flux yang sedang meningkat itu. So external flux sedang meningkat. So dia nak menurunkan dia. So that's why it produce opposite flux. Flux yang di luar tu adalah ke dalam kertas. So flux induced by the coil is out of the paper. Dia macam nak opposite direction supaya dia kena cancel flux yang meningkat itu. Okay, so now look at 3 to 4. 3 to 4 pula. What happened to the flux external? What happened to the flux external? Come on. Kamu bercakap dengan orang lain memang begitu kah? You cakap dengan kawan pun, kawan kamu pun akan tunggu 10 minit baru jawab kamu kah? Memang lambat kah? You bukan orang yang you on normal kan? Normal kalau normal you terus bagi respon kan? Takkan you nak tunggu lagi nak respon? Apa ni? Kalau ini 3 to 4, what happened to the flux external?
Clockwise.
Reduce
kan? The flux external that passes through the coil menurun kan? Sebab dia dari banyak flux menjadi tiada flux kan? Betul tak? Yes or not? Yes pun tak boleh.
Ya, betul.
Betul sir.
Betul lah. Flux menurun. Flux menurun. So sekarang the changes of flux is menurun. So Lenz law says oppose the change. Want to oppose the change. Menentang penurunan ini. Macam mana dia nak menentang penurunan? How to tulis balik ini, copy paste saja. How to oppose the changes, how to oppose the decrease. So kalau benda ini menurun, dia tak mau dia menurun, dia sebaliknya nak meningkatkan. He try to increase back the flux. Tadi ialah apa? Decrease kan. Sekarang he try to increase the flux. Dia sengaja menentang. Sesuatu benda yang sedang meningkat, dia nak menurunkan. Seluruh benda yang sedang menurun, dia nak meningkatkan. Dia menentang perubahan. Oppose. Maybe I should write that. Oppose changes. The word menentang perubahan. Menentang perubahan. Tak? Menentang perubahan. Oppose changes. Oppose changes. Yeah. So he try. Yeah. Should highlight this one. Okay. So kalau flux dari 3 ke 4, flux sedang menurun kan? So kalau flux menurun, dia tidak mau dia menurun. Maksudnya coil tidak mau dia menurun. Dia tidak mau dia menurun. Dia menentang penurunan. Ya. He try to decrease the. Ya. He try to oppose the decrease. To oppose the decrease means he want to increase back. Kalau sesuatu benda itu menurun, macam mana nak menentang penurunan tu? Dia nak meningkatkan balik. Betul tak? Dia nak meningkatkan balik. Seolah-olah perubahan itu tak pernah berlaku. Okay? He try to increase back the flux. So how to increase back the flux? He produce apa? Must be produce same direction flux. Produce same direction flux. Kalau flux menurun, ya, that means flux yang ke dalam ini hilang, dia nak tambah balik macam itu. Dia nak tambah balik. Tambah balik, macam mana tambah balik? Mestilah produce same direction flux. Flux induce ini atau flux from the coil ini adalah ke dalam. Ini flux from the coil, that means this flux is generated by this coil. But how does this coil generate the flux? It must have induced current first. Dia mesti ada induced current dulu, baru ada induced flux ke dalam. So now use your right hand grip rule. Find the induced current direction. Use your right hand grip rule. So your thumb shows direction into the paper. Okay, your thumb shows direction into the paper. So now your finger point in what direction? Your finger point in what direction, class?
Clockwise, sir.
Clockwise. That's right. That's why it clockwise. That's why it clockwise. Itulah. Ya, menentang perubahan. Lenz law is all about opposed changes. The word of opposed changes is very important. What do you understand by opposed changes? It doesn't mean that the opposed doesn't mean that the flux is always opposite direction to the external flux. Yeah, remember the word oppose changes. The word oppose here doesn't mean it does not mean the flux induced always what? Always opposite direction. Always opposite direction with external flux. It doesn't mean the flux induced always opposite direction with external flux. The flux induced can be same direction also. The flux induced can be same direction also with the external flux. Dia bukan maksudnya flux induced sentiasa opposite direction, bukan. Flux induced can be same direction with the flux. Apa yang oppose changes di sini bermaksud menentang perubahan. Menentang perubahan. Kalau benda itu sedang meningkat, dia cuba nak turunkan. Kalau suatu benda itu sedang menurun, dia cuba nak meningkatkan balik. Macam suatu benda yang wujud tiba-tiba, dia cuba nak cancel balik supaya balik kepada macam asal. Yang tiada, ya. Dia macam hasilkan opposite direction flux supaya cancel balik supaya dia kembali kepada keadaan asal. Nak kembali ke keadaan asal. Ya, like this one, tiba-tiba benda ini hilang, ya, tiba-tiba benda ini hilang, ya, flux eksternal itu hilang, dia cuba nak tambah balik supaya balik kepada keadaan asal yang, ya, ada flux into the paper. Understand? That's why they produce same direction flux. Yeah. So you understand this one? If you understand about opposed changes, after that you use your right hand grid rule to find the induced current is not a problem. You can easily find out this one is anti-clockwise, this one is clockwise. So that's all about Faraday's law and Lenz law. Okay. Later we will use Faraday's law to calculate a certain value, yeah, to find out the induced EMF, yeah, and induced current, yeah, in tutorial questions lah, yeah. We will use this formula. We will learn how to use the formula. And important thing is Lenz law. You must understand betul-betul. What is mean by opposed changes? Opposed changes means when the flux increase, the coils try to decrease back the flux by producing opposite direction flux. If the flux external is decreasing, the coil tends to increase back. Trying to increase back the flux. So that's why he produces same direction flux. That is mean by Lenz law opposed changes. Okay, kelas? Masa pun sudah almost habis. Boleh faham, kelas?
Boleh, sir.
Ya.
Boleh, sir.
Faham dan ingat dan rajin buat soalan. Bukan faham saja lepas tu selesai tugasan. Itu bukan formula untuk berjaya. Formula untuk berjaya ialah dari saya hanya 40% yang input. 60% itu usaha sendiri. Itu sebenarnya. Ya, kejayaan bukan datang dari saya, datang dari kamu, ya. More than half is from you. Okeylah, itu saja. Terima kasih.
Thank you,